And the question is really, first, what do you want to measure? And what goes with that question is why you want to measure things, because depending on what you want to do, whether it's with bottom sediments or surface things, the answer can be very different. And again, yeah. So I'll talk about different wave properties, how we can measure that with pressure gauges and surface buoys. And I'll say a few more things about other measurement devices, but you can really go into the chapter 3 of this. And there's more details about other things. And tomorrow, the satellite part will be covered tomorrow, so it's all in there. So again, the obvious things we see about waves is the fact that the surface moves, right? But that's only one variable, which is the surface elevation going up and down. There's obviously also velocities of the water and also of the air. There's variations in pressure. You can be interested in drift, in the energy, in the shear stresses, which are important for air sea fluxes, in the surface slopes for remote sensing, or many other things, or bed shear stresses for sediments also. So there's many things you can think about measuring. And one way to go about all that is ideally, the ideal thing here means we're going to consider that waves are linear and first propagating over a flat bottom, and they're also irrotational, meaning that there's no vorticity in the fluid. If not, then that will introduce some complications, but that, some of that discussed in the book. We'll leave that alone for today. And in this framework with linear waves, irrotational waves on the flat bottom, one of the nice things is that if you're measuring any of the properties of the waves, there's a link with other properties. And for example, if your wave quantity, I call it A, is some function m times surface elevation, then the spectrum of that quantity, could be velocity, could be pressure, could be anything, is just this function squared times the spectrum of the surface elevation. So you can use it that way to transform surface elevation into something else, like velocity or pressure or anything. You can also invert that relationship and measure the something else, the pressure, the velocity, or whatever, and then invert the elevation from that. And this is actually what's done by most measuring devices. And so, for example, if you're looking at surface elevation for linear waves, it's just A times the cosine of the phase. Then the velocity below these waves is this function times the cosine of the same phase. And so this red box here is the same as my m coefficient here. And so you can have the spectrum of the surface elevation, maybe what you want, as a function of the spectrum of the velocity, which is maybe what you're measuring. Or vice versa. If you're actually measuring elevation, you want to know the velocities, then you can apply this transfer function. And yeah, so in the absence of currents, you may want to use this relationship between the wave radiant frequency and the wave number, because for some of these functions, sometimes you need to have the k, sometimes you need to have the frequency, or both. If you have current, you have to be careful that this is not, this sigma is the same, but then you have another frequency, omega. And so in presence of currents, usually we make the difference between sigma, which is an intrinsic frequency. Maybe the black was working better. Sigma here in my slides is what I call the intrinsic frequency. And omega is what I would call the absolute frequency. This one is what you measure with a fixed instrument relative to the ground. And it is equal, and so omega is equal to sigma plus the Doppler shift effect plus k vector dot u. So there's a vector product between the wave number and the current vector. So if you have current, the frequency you're measuring in a fixed frame of reference with an instrument fixed on the ground, for example, is not the same as this intrinsic frequency, which is a frequency in a frame of reference moving with the current. And this is typically the frequency that we will use in the wave model, in WaveWire 3. We work always with that. And for example, when we have the spectrum E of f and theta, the f actually corresponds to this guy. But when you actually measure, very often you have a moored instrument, and so you have to work with that guy. Okay, so there's a very clear difference between the two frequencies, which are not the same. Well, if the currents are very strong, actually buoys have problems. These days we also work with drifting buoys, but you have to go in and put them back in and pull them out, so it's quite a bit of work. But if you have like an ADCP or something at the bottom of the ocean, it's not measuring the same frequency, and so the difference between these two can introduce a lot of confusion. So you have to.
Sorry.
Yes.
What's the difference between the bold K and the regular K?
It's the same K.
Same K.
Same K. What's different is the two frequencies. Omega in the absolute frame of reference, fixed to the ground, and sigma in the frame of reference.
No, I mean the K and at the U. That's bold K and.
Yeah, okay. K is a vector. It has two components, so K in X and Y component, if you want. And so this is a vector, this is a vector. This is a norm of this. Okay, so when I write K here without the underline, it is a norm of the vector. And because I cannot make it bold like that, so in my slide here, this K with a vector is actually bold. Okay, so K with a bold K is a vector. So this is a vector velocity, and this is a vector K. Okay? So that's the story. So we are assuming linear theory, rotational waves, and we can basically convert anything from the surface to the bottom or vice versa. And this slide is just to insist on these two assumptions. The first assumption, rotational motion, that kind of works most of the time, except in the surf zone, which it can be a problem. The fact that the motion is rotational or not rotational comes from the shear of the current, the vorticity of the current. So when it is rotational, which applies most of the time, you can really convert anything from the surface to the bottom with these functions, x and or cosh in general. And that also applies for nonlinear waves. So the other assumption is that waves are linear, and then when waves are linear, then we have this connection between f and k from a dispersion relation. And so there's some part of the wave spectrum which is not quite linear, like the high frequency part, where you may want to do something a bit better, and then you actually may need to have a 3D spectrum, not just a 2D spectrum. So it's a bit more complicated, and it carries much more information. But most of the time, you can compute the 3D nonlinear effect of the spectrum just from the regular 2D linear part of the spectrum. So waves are nonlinear, but they are weakly nonlinear. And there's a way to go around these two assumptions if you have to. But when things are simple, linear, irrotational, and so we're going to look at a very simple instrument, which is a pressure gauge, so measuring the pressure. And so this pressure is measuring time series, and actually this example I was showing before is from a pressure sensor that was, so it's this, I should have shown the pictures, it's an OSSI, maybe I have it, no I don't have it. It's a pretty cheap pressure gauge. You can install it on the bottom, on the seafloor, on the frame, on the rocks. Here it was bolted into the rocks on the cliff, and we measured this kind of time series of pressure, and from the pressure you can convert to the surface elevation, and you just apply what I was showing just before. You need to apply this relationship that the pressure is some coefficient times the amplitude of the surface elevation. So essentially you have this coefficient here, which is transforming the surface elevation to the bottom pressure. When z equals minus h, this goes to 0, and so we have 1 over cosh kd, which is attenuating the surface elevation to be the pressure of the seafloor. And of course, the rho g here is to go from elevation to pressure, but this so that's, yeah. And so in practice, to compute a spectrum, there's a few steps you have to go through. One I will not talk too much about, but could be some issue in some cases, is that before you digitize a signal, you typically want to remove the high frequency part, which otherwise get aliased into your frequency domain. For waves, if you're actually resolving the dominant waves, the peak of the wind speed, you have much more energy at the dominant waves than you have at the short waves. So if you don't do this anti-aliasing filter for the short waves, often it's not too bad. And once you have digitized your signal, so you have a time series with measurements at discrete intervals. So that's the case here. This is a case of stereo video data, which I have elevation of the sea surface at a given point and as a function of time. And I have 12 measurements for each second. And so this time frame corresponds to 1,000 measurements. And in that case, you can see that, for example, you start here at the beginning and you finish there at the end. And so the value at the end at the beginning is not the same. And when you apply a Fourier transform to compute the spectrum of that signal, what's done usually is to apply a discrete Fourier transform. And so discrete Fourier transform is actually the Fourier transform of a signal which repeats itself, which means that you take the signal, you put it here and here and here again. And when you do that, you have a jump from here to there, which is just like a delta function. And this jump will introduce some spurious high frequency in your signal. And so this is a black line here is a spectrum of the signal. You have this high frequency level of an energy here, which is not real. It's just the artifact of this jump between here and there. The rest of the spectrum looks more or less the same. It's different because it's actually the waves are random, so the spectrum is random, and so So to correct for that effect, what's done is to apply a window. So you take your signal in black and you multiply it by a window to make the value 0 on both sides, so that it will be continuous. So here I use a Hahn window, which is just a raised cosine shape. And then you can compute the FFT, and then you get this spectrum here in red. And so you see the big difference here, and that was due to the artifact of this jump between the beginning and the end. And of course, we will tell you, well, but these two spectra look very, very different, right? So it looks really random, and that's because yes, the waves are random, and to get a better spectrum, we need to average the spectra. Basically, waves are almost Gaussian, so any measurement of the sea surface has a variation which has a Gaussian distribution. And when you take the Fourier transform of a Gaussian field, you get a Gaussian distribution of the Fourier amplitudes. So your Fourier amplitudes are Gaussian also. And so if you take one record or the next record, they will have different amplitudes, which is random. Now, if you only take one spectrum, and so for example, I take a small piece here, and I multiply by this window here in blue, and I'm going to look at the spectrum of that, and that's one of these blue curves. I get one spectrum. Then I can take the green part here with the window, get another spectrum, okay, and I do that for all these windows, and I get all these different spectra. What I can do now is to take the average of that, and that gives me the black line, and you can see it's much smoother. And what I've drawn over that is, so I have the dashed line and the dotted line and dashed line, and these correspond to confidence intervals of these different spectra. The dotted line is a confidence interval for a single spectrum, and theoretically it follows a chi-square distribution with 2 degrees of freedom. And you can look up in the table in the book, and you will find the numbers for this chi-squared with 2 degrees of freedom. So it's this funny-looking table. And so if you define a threshold for the confidence you want to have at 95%, so here it's 95% confidence intervals. Want to know if you want to be more accurate than 95, you can use 99. So you can use that table and look at what is a coefficient that multiplies the spectrum to give the confidence interval around it. But the basic idea is that waves are random, so the spectra are random. And a single spectrum has a variation of 2 orders of magnitude. Okay, so at a given frequency, you only know the spectrum within a factor 10. Okay, so you need to average the spectra a lot to reduce that interval of confidence. And so here I use, so I have these 21 windows. I have 21 independent samples. And that gives me 42 degrees of freedom because the spectrum has phase and amplitude. So this way you get twice as much number of windows. And the interval of confidence for 42 degrees of freedom is something plus or minus 40%. So when you do that, if you can average all these spectra together, you can know the spectrum within this confidence interval. And that's, again, the confidence interval at 95% confidence, which means that there's one spectrum out of 20 which would be outside of these bounds. And this is what you see, these dotted lines actually, some of them, there's actually one or two spectra that fall outside, and that's because actually I have 21 windows, but also I have I also take windows which are shifted by half, and this is called the Welch method. And that's because when you take the window, you actually are losing that information, so you want to take that information, you also take the window again, you shift it. So I have 41 estimates of the spectrum, and from statistics, I know that I should have, on average, 2 spectra that fall outside of these bounds, and this is what you see. So the theory works pretty well. We have 1 out of 20 spectra, which means 95%, is inside, but yet there's 5% outside, which is 1 out of 20, fall outside of these bounds, and so this is because waves and spectra are random. So when you're comparing observations from 2 different platforms in the same sea state, you never get the same spectrum because you get random realization of the sea state. Okay? It's only if you put the instruments exactly on the same platform, so they move together, then you should get exactly the same spectrum. But as soon as you put them in the same sea state, but not the same point, then you get these fluctuations, which is the same as looking at one piece of the record and the next piece of the record. Okay? And so as a result of that, that's one of the main reasons why there's uncertainties and error bars on all wave measurements, because we don't, we're dealing with a random process, and this is life with random fields. What should I say about that? Yeah. So of course, to make it this more narrow and narrow, what you'd like to do is to average a lot, and there's 2 ways you can do that. You can make smaller windows to have many more windows, okay, and then you have a more narrow error bar. But if you make the window shorter in time, what you will lose is spectral resolution, because your spectral resolution, the spacing of these points in frequency, the delta F, is equal to 1 over the length of the record. And so here, it's about 100 seconds. And so my delta F will be 0.01 hertz. If I make it shorter, if I make it 50 seconds, my delta F will be 0.02 hertz. And so I'll have a few more points in F. And so at some point, I will not be able to resolve the difference between this peak and that peak if I only have like 1.01 hertz there. So there's a trade-off between the spectral resolution, delta F, and the accuracy you want of the spectrum. That's one constraint. Or, if you are lucky, maybe the sea state stays the same and you can record longer. And then instead of this is only 20 minutes, you could go for 1 hour, 2 hours, 3 hours. That is if the sea state is stationary. Now, in the laboratory, you can do this. You can do the same experiment again and again and again and do lots of averaging. In nature, you don't always have the choice. Here, with the tidal currents, the sea state changes every hour. So beyond 1 hour, it's becoming a bit funny to look at average spectra with the tides doing some funny things or the wind turning. And so typically people advise, and WMO and all the, so the minimum you should do for wave measurements in the ocean is typically 20 minutes. And that's related to the number of waves you have. So if you have longer wave periods, you should typically do a longer record. If you have very long swells, because you have less waves, so statistics are not so good, you may want to go longer. But on average, people consider that a good measurement is 20 minutes. when I compare to the model, I usually do 1 hour averages and make sure I have continuous data for 1 hour. And then it depends. I mean, some buoys only measuring 20 minutes every hour. I think the NDDC buoys still do that. Or at least it was doing that some time ago. Maybe they've changed that. But and so the uncertainty and the error bar you have on the spectrum really depends on the length of the record you're averaging and how much data you can put in this. Okay? So waves are random, and we have to deal with that.
I have a question about windowing.
Yes.
I mean, this is an old question I had from when I was working with the images. When you light a window, for example, in this example, the way you are showing that there,
Yeah.
Do your windows affect the animations or only the start
And the end.
at the end?
Yeah, like this. So the window signal goes to 0 in red, and so at the end it's not the same as the black yet. In the middle it's the same.
When you light a window, you try to make it equal at the beginning and at the end.
Yeah, this is to avoid this kind of problem.
Yeah, I know that. Okay.
That's the reason. Some windows actually don't go exactly to 0, like the Ham window is not exactly 0, and it has better properties for the side lobes. And yeah, what's happening when you actually do this kind of processing, so you have an original signal and you change it by windowing, averaging, whatever. If you multiply your signal by something, then the spectrum is a convolution of the real spectrum by the spectrum of the window. So the Fourier transform of a product, which is this kind of product, is a convolution of the Fourier transforms. And so when you know so you can do different type of windowing. The most stupid window you could think of is what people call a boxcar window, so just a square top hat. This is very bad. So if you take a window like this, this is not good, and I'll explain why. So most windows are smoothly going up and down, and what you want is, as Matthias was saying, you typically want to have the same value here as there, and as close as possible to 0. If you multiply by a window like this, as I told you, the Fourier transform of that window is a sinus cardinal function, so it has all sorts of funny side lobes. And so as a result of that, the peak of the spectrum will make some jumps, and it's not looking very good. So there's like 20 different windows you could use, and they have different properties. The Hanning window I'm using here is like the most simple thing. It's pretty good for most applications. So there's windowing, there is averaging, and there's one thing I skipped here because I was working with surface elevation. The data I had here was measurement of surface elevation. So I was computing a spectrum of surface elevation from measurements of surface elevation. In the case of a pressure gauge, I have pressure at the bottom, and I need to convert the pressure and multiply by this function to go to the surface. And this is where you need to worry a bit more about the noise. So these are some examples of time and frequency measurements of pressure. This was in 60 meter depth offshore of the coast here. The linear wave signal is this. And so you can see that the signal goes from, this is a log scale, so there's like a factor 100 in energy from here to there, and another factor 100 from here to there. So the signal here is like factor 1,000 less than the main signal there, but there's still some things. And when you transform the pressure signal to the surface, you're multiplying by a function which is exponentially growing with frequency. So at high frequency, it's a super big number. And so at some point, you're going to amplify the noise, or something which is not real noise, but actually some wave signal which is not linear. And so if you have any nonlinear wave effect, which is this stuff here, and you multiply by a big number, then you get some crazy values of surface elevation. So you have to be careful when you convert bottom pressure into surface elevation. At some frequency, it's going to work until some frequency, and at high frequency, it's not going to work because you just have some noise. And this is what you will do this afternoon in the tutorial on that. And oops. So that's a story about pressure measurements or sea surface elevation measurements. We have spectra, we have random issues, we need to worry about averaging and spectral resolutions. So if you actually design the instruments and the measurements You have to keep that in mind. If you're using the data from somebody else, you don't have to worry about it because they've done it. But you have to know that there's some uncertainty in these spectra and some uncertainty in all the parameters which are due to the random nature of the ocean waves. So that was 1D spectra. And what I want to talk to you now before go to database stuff is the 2D spectrum. So I was showing this kind of plot before, in which we have energy as a function of frequency and direction. And this is typically what we would like to get. And this is actually the kind of thing that we compute in a wave model that we're going to run. So the wave model is actually, like WaveWatch 3, compute the evolution of that spectrum in space and time. And what we is actually measured by a buoy. So, for example, a wave rider buoy. It is a 90, so it's different diameters, but this one is, I think, was 90 centimeter diameter, this big. We're deploying it from a ship. This is a 3-meter discus buoy from NDVC. So this guy is measuring X, Y, and Z displacement. Its measurements are made actually from accelerometer. So what inside of this buoy is accelerometer, which is on a gimbal. So the gimbal is following the rotation motion of the buoy so that it always stays up. So the buoy is going around this gimbal. And what you're measuring is the acceleration in the Z vertical, what is called the heave, and the X and Y accelerations. So you have 3 time series, and you integrate these time series to get X, Y, and Z displacement. And that's what you get from that. And this is an example of time series X, Y, and Z from this kind of buoy. So you can see X in red, Y in blue, and Z in black. And actually, just from the phase shift of different curves, you can tell the direction of the waves, and I will tell you why. These buoys and deep sea buoys measure the heave and also the 2 angles, pitch and roll. Okay, and this is many of the buoys around the US are based on that design with different sensor packages, but basically measure this acceleration and the 2 angles. And again, you have 3 time series. So they will look a bit different like that from that, but it's the same principle. Same principle because from 3 time series, you can compute 6 parameters at each frequency. So first of all, from each time series, you can make a spectrum. So from the vertical elevation, you make a spectrum of the vertical displacement, like I was showing before. Okay, that's what I call easy here. And this spectrum of the vertical displacement is just the sum of the directional spectrum over all directions. Okay, all waves in all directions contribute to vertical displacement. Now we also have the spectra of the X and the Y displacements. And if you go back to linear theory, you can actually transform the spectrum of elevation to horizontal displacement X and Y. And you see that you have a 1 over tanh kd that comes in front. And you have X displacement gives you cosine squared and Y displacement with a sine squared. And so basically, these 3 spectra are related to the integral of the directional spectrum with some coefficients with cosine and sine. So these integrals, we call them moments of the directional spectrum. And on top of these 3 spectra, you can also compute what's called the co-spectrum. And the co-spectrum is a complex quantity, which is just the Fourier transform of one quantity times the complex conjugate of the Fourier transform of the other quantity. So if you take the X spectrum and the Y spectrum, you mix them together, and you get the co-spectrum. The co-spectrum is not complicated. It's just the spectrum of the correlation function. So when you have, if you take the spectrum, it's the autocorrelation function of X with itself. If you take X and Y or X and Z, is the correlation function of X with Z. So you have correlation of these 2 variables, and you take the Fourier transform of that. It will tell you at which frequency these 2 time series are correlated. And because it's a complex number, it has an amplitude and a phase. The phase of the co-spectrum is just the phase shift of the 2 time series at a given frequency. So for example, if I go back to my time series here, you can see that the black maximum is before the red maximum. So you have a clear phase shift between the black and the red. And so that will translate as a co-spectrum between the black and the red, which is essentially a quadrature and so you have a phase shift of 90 degrees between these two things. And the co-spectrum of these two here has this complex I here. So this stuff is typically in quadrature. And the sign, so this can be positive or negative, that integral here. If it's shifted one way or the other way, and we can think about it a little more. So here you can see that the x is maximum after the z. So imagine the buoy is going around like this. So it's going up and then forward and then down and then back. So if it's doing that, it's going, the maximum of z is happening before the maximum of x, okay? Which is exactly which is here. So that's one possibility. The other possibility is the wave goes like this. So the maximum of z would be after the maximum of x, which is here, so it would be negative here. In that case, the wave will be propagating the other way. So because it's like this, we know the waves go like in that direction. So this phase shift here tells you the wave propagation direction in x, but also the phase propagation direction in y. And here you can see that the y is much smaller than the x, which is telling you that if you look at it from above, so you have the buoy, which is doing something like this, oscillating. So you have x and y. And the oscillation in y is smaller than the oscillation in x, which means that the orientation must be more towards the x-axis than the y-axis. So this is telling you that the waves are coming almost from the west, and with a little bit, and then you have to look at the sign, it's actually coming a little bit from the southwest. So this is how we tell the wave directions, just from the phase relationship between these and the magnitude of these correlations. And mathematically, we do that with a co-spectrum. So co-spectrum of x and z, y and z, and x and y. And these are all a function of the frequency, so we have 6 parameters. Okay? From 3 time series, we get 6 co-spectra. Now, what do we get from that? You can rearrange these parameters in different ways. And for example, you can take EZ and divide it by EX plus EY. And you see already that if you take EX plus EY, you have cosine squared plus sine squared, because it would be always equal to 1. And so this ratio is actually not a function of direction at all. And in theory, it should be all equal to this tanh KD function. So it's only a function of water depth. It tells you if the ellipse of the motion is flat, like in shallow water, or it's circular, like in deep water. In deep water, this should be equal to 1, and in shallow water, it's something smaller. And so this quantity is also called the check ratio. And some buoy providers give you this data. Like kind of CDIP gives data with not only these first 5, but also this one. And from the 6, so one is just this ellipse business, and the other 5 are really related to the directional spectrum. And so this is what we call the first 5 moments. And actually, these are the first 5 Fourier coefficients of the directional spectrum. A1 is integral of the spectrum times cosine, B1 with sine, A2 cosine 2 theta, and B2 sine 2 theta. And the sum without any cosine we call E of f, or you could call it A0 if you want. And so these first 5 coefficients is all we can get from a buoy about the directional spectrum. Nothing more.
Question?
Yes?
The last cost spectra, XY, what kind of information we can get from this?
So that's correlation of x and y, and so it's integral of the sine times cosine. So if you actually develop this sine theta times cosine theta, you will see that it actually goes into these two. And actually some buoy measurements, if you're not measuring the vertical motion, but if you're only measuring horizontal velocity, for example, if you had GPS velocities, so some buoys only use GPS velocities. In that case, you cannot get this. You only have that. And then you have only 4 numbers. And from 4 numbers, you cannot get these 2, but you can still get these 2. And so if you have a GPS buoy that only uses velocities, or also a tilt meter, like I was showing before, with just the slope, not the heave, you can still get some directional spread and mean direction from these A2 and B2. So some funny systems do not have these 2, but normal buoy typically has these first 5.
what you can do if you have only A2 and B2?
You can do a mean direction and spread from A2 and B2, which is defined slightly different from the mean direction and spread from this one. Okay, that's what we get from a buoy. So this A1, B1, A2, B2, they are nice, but when you look at the numbers, it doesn't tell you much. So I know CDIP love to store them as A1, B1, A2, B2. So if you download data from CDIP in California, they will give you that. But what I prefer, and that's what we've done from GlobeWaves, is to convert these A1, B1 to a mean direction and spread, and I will explain what it is. So these, essentially, the mean direction is just the direction of the vector A1, B1, and the spread just tells you how if there's actually a lot of energy going in opposite direction or with different directions. And so the spread goes from 0, which is a value if all the energy goes in same direction, to square root of 2 in radians, which is 80 degrees in degrees. And this value is maximum when you have the same amount of energy going in the opposite direction. And you can see that you can go back from sigma 1, theta 1, you can recompute A2 and B2, so that it's a bijective relationship, so you can invert and go from A1, B1 to sigma 2 and theta 1, sigma 1 and theta 1. And you can do the same with B2 and A2. You can define a mean direction and a spread from A2 and B2. Okay. And so what we've done with GlobeWave is actually we stored the data in that format with these variables, which is, and we have reprocessed all the data from CIP and DBC, the Canadian buoys, and all these stuff, which have different conventions, to put them all in the same theta 1, sigma 1, theta 2, and sigma 2. And the reason for that is that when you look at the numbers, it tells you a bit more than just, oh, yeah. If you have only A1, you need to look at B1 to know what the direction is. If you want the mean direction, just look at theta 1 if you have something that you can play with. And I guess this is what's going to be used for CMEMS for the Institute TAC, but I think so. We'll see what comes out of CMEMS when the product comes out. So that's what the buoy gives. Again, maybe you wanted to have this nice plot at the beginning. And so in this nice plot, I actually have energy every 10 degrees, which means that I have 36 numbers at each frequency. But we only measured 5. So to go from 5 numbers to 36 numbers, you have to make up 31. And when I say make up, it's really make up, just invent it. And you can use whatever method you want to invent it. So one nice method is called the maximum entropy method. I like that because it's pretty fast to compute, just like 10 lines of code. But it's still possible to make bugs in 10 lines of code, which I found out again yesterday. So I have 3 versions of the code. I have one in Fortran, one in IDL, and one in MATLAB. And somehow my MATLAB version was not working anymore yesterday, so okay, we'll fix that. The good thing with the MEM is that if you compute a spectrum, so a spectrum would be like a function of the directions. You need values at each different directions. If you recompute the moments from the spectrum, so you recompute A1, B1, A2, B2 from the spectrum you have estimated, then you go back the moment you put it in the method to begin with. So the MEM is nice because it actually gives you the exact same moments as the one that you started from, which sounds obvious. But there's another method called MLM, which doesn't do that. So there are still people using MLM. I don't know why. So MLM is the maximum likelihood method. And MLM gives you 2 broad spectrums. So when you compute the spread from the MLM, you get a spread which is bigger than the one you had in your measurement. So I don't know why, but please don't use MLM because the spectrum is just too broad. So MEM is nice, but again, we are really making up numbers. So you could find some other method to give you something different, which would still be good enough. And really, it makes no sense to store the data in the spectra from buoy because you just multiplying this space by a factor, 4 or 5. So it makes no sense to store the buoy spectra as a 2D spectrum. You just compute it as the moments, and then when you want to plot it, then you plot it. But otherwise, it's just inventing numbers. And so this is what I've done here. I invented the numbers so I can make a plot. And so this is coming from a NDBC 3-meter discus buoy, pitch and roll. And when you actually look at the spectrum, you see you have a peak here in the swell, and you have some bit of energy here, which is lower by a factor maybe 100, but there's still some energy here and there. And this, I don't think that's real. I think it's just because the measurement is noisy. And when you put a noisy measurement in this kind of method, you will try to make, fit with and actually that will enhance the spread artificially. But that's just because the spread provided by the buoy is noisy and maybe is biased high. And it's actually a nice discussion by O'Reilly et al. Of the noise in the 3 meters discus buoys, which is, I think, is a bias of 5 degrees in spread from that paper. And the people at NDBC, they hate Bill for that, but because that's a buoy they've been using everywhere for 20 years. The reason they did these big buoys with a nice thing like that is that they don't want to measure just waves, they also want to measure winds and other meteorological things. If you don't only want to measure waves, this is much better, but then you don't have winds. So that's...
Okay. That spread equation you showed us,
yeah.
that's degrees with respect to the main direction?
No,
Or is
it's...
or is it like a standard
So
degrees?
If you have a narrow spectrum with a Gaussian shape, it is actually the half width of that Gaussian. If you have 2 peaks or a funny shape, it's just a number.
So it depends on how you're analyzing the spectrum. Because you can separate. If you got many peaks, you can separate and analyze only one peak, for example, the main one, and then you have maybe a smaller
so
spread.
what I could have done, and maybe I'll do that for tomorrow. If you actually have, if the real spectrum has 3 peaks at the same frequency, so you have one bump here, one bump there, one there. From that you can compute A1, B1, A2, B2.
Yeah.
Okay. We do the integral what I showed before. So these 4 parameters. A1, B1, A2, B2. Then you go through MEM, and you get another spectrum. And the other spectrum, maybe will look like this, but you will never get the 3 peaks. Never. Because the MEM method is just trying to fit 2 peaks as narrow as possible to your distribution. That's what the MEM does. And so if there are 3 peaks at the same frequency, with a 1 buoy, you never see it. There are ways to detect the peaks, and this is what's called the wavelet, the WDM method by Mark Donlan et al. So wavelet directional method. So with that, you can detect the peaks, but you cannot make a spectrum. You cannot say, well, that's a spread and like that. This method doesn't give you a directional spectrum, it gives you a directional distribution, which is not the same as a spectrum. If you have some question about that, I'll answer that. But, so the buoy only measures 5 parameters at each frequency. To make 3 peaks, basically you need to know the value of each position and then the width of that. So that for that you need 6 parameters. You don't have 6, you only have 5. And that's a problem with buoys. What we are lucky that very often we only have 1 or 2 peaks at the same frequency. So in most cases, the spectrum looks like the real spectrum, but it may be, when you go through MEM, that the spectrum you reconstruct can be very different from the original spectrum. It's possible, and you don't know it. And that's because buoys don't measure directional spectra. Buoys measure only 5 parameters. That's what I wanted to say. So that's buoys. What else do I have? Oh yes, few things about the...
Can you fake it by analyzing different frequency bands, for example?
No, well, that's again frequency. No, the only way you can fake it is by analyzing different time segments, and that's what's done in WDM.
Okay.
If you actually take a very small record and you only fit one direction, if you are lucky, then at one time you'll hit that peak, later you hit that peak, and later on you'll hit that peak, and then you are able to detect the peaks with WDM. It's a very good peak detector, but it's not the same as a directional spectrum. Just a few things, yeah, about the buoys. Buoys are not measuring the waves. Buoys are measuring the buoy motion. And between the buoy motion and the wave motion, It's not exactly the same. These are examples of 3 spectra measured with 3 different hulls from data well buoys. So the old hulls had this 90, almost 1 meter diameter, and now they're making smaller 40 centimeter diameter with GPS measurement. And this is a spectrum with frequency. You can see that the spectrum look all the same up to around here, which is around 0.7 hertz. And actually, this is one reason why the data well buoy spectra stop at 0.68 hertz. Because beyond that, at some point, the size of the buoy is actually becoming comparable to the wavelengths. And so the buoy is not following the small waves. You can see that the small waves, they should be here, but they're down there. And if you make a smaller buoy, you can measure smaller waves. And as you go from 0.9 to 0.4 meter, that's a factor 2 in wavelengths. But factor 2 in wavelengths is only a factor squared of 2 in frequency, so it doesn't buy you a lot, but you can get a little higher in frequency. So we played that game in the lab. We actually developed a new buoy to measure smaller waves, but still you have to be able to recover the buoy. And so if you make it very small, it's a problem to get it back. And so we ended up with something which is like this. And so we get good waves up to 1 hertz. And for some remote sensing application, that was nice. But and this is this is a check ratio, or the inverse of what I was showing before, which should be 1 deep water. And you can see that as you go towards 1 hertz, you have these resonant peaks. And if you go on YouTube and you search for data well wave buoy, they have a nice video of a wave which is excited at the resonant frequency. And with small waves, you can make the buoy jump up and down if you're exciting it at the resonant frequency, and you have this resonant peak here, which is due to this resonance of the mechanical system of the buoy. And one word about climate. These 2 plots. This one is from a paper we're writing now with Justin Stopa on looking at long-term trends in the climate. This is using data from the NDBC buoy 4201, which is in the middle of Gulf of Mexico, if I remember correctly, from 1980 to 2016. And this is showing the difference between the mean value of the model and the buoy. So the model has problems, and I'll talk about that more tomorrow and this afternoon, because we're forcing with different winds. But the buoy also has issues that they've changed the system on the buoy at different times. So here they was using this MYX whatever system. Then at some point they went to a UDAX system and the DVIP thing, which are different accelerometer design, and some are strapped down, some are on the gimbal, some are different things. And potentially some of these jumps in the bias against the model are due to these change in the payload, the instrument actually measuring the waves. And we have metadata until 99, and after that we don't have the metadata. So God knows what happened to the buoy. And right now NDBC is actually changing all their buoys to go from these 3-meter discus aluminum hulls to new foam, smaller things. And we don't know what's going to happen to the wave climate, but it's quite possibly that we get a wave climate change due to the buoy change in the coming years. This is a lot of plots coming from Livermont, who was shown last year at Liverpool, and that's this is the same spot, just the PDF of the wave heights. Of course, different times, so maybe there's a you have El Nino year or something like that to get different. But you can see that this system was not measuring heights as high waves as here, and the high part here is more or less the same, but the maximum and the mode of the PDF looks really funny from the different type of sensors, and yeah, so there's a lot of work that has to be done to check on the impact of changing the hulls and changing the sensors to get trends within 1 centimeter per decade or per year, which I think is what's required for climate applications. Yes, I have to stop. One thing I have to say, I talked at some point about conventions for directions. So again, all my plots are showing direction from. Obviously, other people are using direction to, so you have to be worried about that. And as I said, when you work on the coast, people, and CDIP is one example, always using direction from. Also, apart from that, everybody is usually, when you when you make the plot, it's easy. You can see the plot. When you give the numbers, you have to be careful. What's a convention? And so most people use this nautical convention, which means that 0 is north. So you have 0, 90, 180, 270. And it's turning clockwise. So usually everybody using that. But when you're making computation, cosines and sines, people are actually used to trigonometric convention. It would be 0 here, 90 here, 180 here, and 270 here, going this way. And so when you actually look inside the codes, and that's the case of WaveWatch, it's using that. So just be careful not to be too confused. If you're actually looking inside of the code, at some point it's working with something like that, and at some point it's converting it back to the other convention. So that can be the source of lots of fun, because you have to choose the origin, you have to choose which way you turn, and then you have to choose from or to. So you have 8 possibilities, and there's 8 ways to get it wrong, or 7 ways to get it wrong, and only one is right. So just to let you know, and I was scratching my head yesterday again with that when trying to make my MEM work, and I'm going to skip that. And just to summarize, yes, waves are random, measured spectra are uncertain. So we have some theoretical, some theory to tell us what's the uncertainty on that based on the record length and how much averaging you've done. Buoys do not measure the 2D wave spectrum, they only measure the first 5 parameters. Be careful of conventions. And we'll play later this afternoon with real data, so then you can also have the fun of formatting the data in many, many different ways. So if you actually get data from CDIP and BBC, the Canadians, they all look at different formats. And hopefully CMEM is going to save our time. And so we've done some of that work as part of the GlobeWave project before, it's still work in progress to get everything in the same format for Buoy. Voilà.